Before we begin, let's look at examples of some common chemical reactions, like the burning of coal. When coal is burned, the chemical energy stored in the molecules is released as heat or thermal energy. Another example is that of burning of fuel in a car engine. When the fuel burns in an engine, it converts the chemical energy to mechanical energy, propelling the car to move along the road. In both the examples, chemical energy, that is the energy stored in the bonds of atoms and molecules, is converted to other forms of energy. Thus, various forms of energy are interrelated, and under certain conditions, these may be transformed from one form to another. The branch of science that deals with the study of different forms of energy and the quantitative relationship between them is known as thermodynamics. The term thermodynamics is derived from the Greek word thermos, meaning heat, and dynamics, meaning flow. It was coined by James Joule in the early 19th century. Thermodynamics deals with the energy changes within a system. A system in thermodynamics refers to that part of the universe in which observations are made. For example, the tea in the teapot is a system. The part of the universe that is not a part of the system but can interact with the system is called a surrounding. In this case, the room in which the teapot is kept is the surrounding. Systems and surroundings together constitute the universe. The part that separates a system from its surrounding is known as boundary. In this case, the wall of the teapot is the boundary. Note that a boundary can be real or imaginary, and it controls the flow of energy and matter into the system or out of the system. In thermodynamics, based on the movements of matter and energy between a system and its surroundings, systems can be classified into three types. These are open system, closed system, and isolated system. Let's look at each system. A system is said to be open if it can exchange both energy and matter with its surroundings. For example, tea becomes cold when left open for some time in a container as a result of exchange of energy with the surroundings. At the same time, some amount of tea escapes from the cup as vapor. This is because of exchange of matter with the surroundings. Hence, this is an example of an open thermodynamic system. A system which permits the exchange of energy but not the exchange of matter across the boundary with its surroundings is called a closed system. For example, if tea is kept in a closed steel teapot, it takes some time to cool down. This indicates that energy is exchanged with the surroundings. However, as vapor cannot escape from the container, no exchange of matter is possible. Hence, this stands as an example for a closed thermodynamic system. A system that can exchange neither energy nor matter with its surroundings is called an isolated system. For example, the tea kept in a thermos flask remains hot and the vapor also doesn't escape out. This is because neither matter nor energy can be exchanged with the surroundings. Hence, this is an example of an isolated thermodynamic system. You have learned that a system is a part of the universe in which observations are made. In order to make these observations, it is important that we know the state of the system. By state of a system, we mean the condition of the system in terms of measurable, macroscopic properties such as temperature T, pressure P, and volume V, to name a few. The first state of the system, that is, the state before the change, is called the initial state, and the last state, that is the state after the change, is called the final state. As a change in the magnitude of these properties changes the state of a system, these properties are called state variables or state functions. In other words, properties whose values depend only upon the initial and final states of the system and are independent of the manner in which the change is brought about are called state functions. Macroscopic properties, on which the state of a system depends, are further divided into extensive properties and intensive properties. Extensive properties are properties that depend upon the quantity of the matter contained in a system. Examples of extensive properties are mass, volume, and heat capacity. For example, 200 milliliters of water takes up more volume than 100 milliliters of water. Intensive properties are properties that are independent of the amount of the substance present in the system. Some examples of intensive properties are temperature, pressure, freezing point, and boiling point. For example, boiling point is an intensive property because whatever be the quantity of water, it always boils at 100 degrees Celsius. When the state of a system changes, it implies that some thermodynamic process has occurred on the system, and energy has been either added to it or removed from it. The energy stored within a substance or a system is known as the internal energy of the system. In other words, internal energy is the sum of all the possible kinds of energy of a system. Internal energy is represented by capital U. The absolute value of internal energy cannot be found. However, change in it, represented by delta U, can be found. Internal energy U changes when work is done on or by the system. Heat passes into or out of the system. Matter enters or leaves the system. Let us discuss the change in internal energy brought out by work done on the system. Let us take a certain amount of water in a thermos flask or an insulated vessel that does not allow heat exchange with the surroundings. Such a system is called an adiabatic. The state of such a system changes without an exchange of heat, and thus the process is called an adiabatic process. In other words, delta Q is equal to 0. We can bring a change in internal energy in a system by two ways. In the first method, internal energy can be increased by doing some mechanical work. For example, by churning the water. Let UA be the initial internal energy of the system at temperature TA. After churning, internal energy changes to UB as temperature increases to TB. Thus, the change in internal energy is given by delta U is equal to UB minus UA. In the second method, internal energy can be increased by the same amount by doing electrical work. In this, an immersion rod is kept in water and the temperature before and after is measured. We find the change in temperature as Tb minus Ta. Hence, the change in internal energy, delta U, equal to Ub minus Ua. Thus, internal energy changes to the same extent either by doing mechanical work or electrical work, which indicates that it is independent of the manner in which the change is brought about. Therefore, internal energy is a state function. If work is done on the system, then U increases and W is considered as positive. On the other hand, if work is done by the system, then U decreases and W is considered as negative. A change in internal energy can also be brought out by the transfer of heat. Heat transfer takes place from the system to the surroundings, or vice versa. The exchange of energy due to temperature difference is called heat Q. Therefore, delta U is equal to Q. Q is positive if heat transfers from the surroundings to the system, and negative if heat transfers from the system to the surroundings. If heat transfers from the surroundings to the system, then internal energy increases, and hence Q is considered as positive. On the other hand, if heat transfer takes from the system to the surroundings, then internal energy decreases. That is, Q is negative. When a change in the state of a system occurs, energy is transferred either to or from the surroundings. This energy may be transferred as heat or mechanical work. In thermodynamics, the only type of work generally considered is the work done in expansion or compression of a gas. This is known as pressure volume work or PV work. Let us understand this better with an example. Consider a cylinder filled with 1 mole of an ideal gas and fitted with a frictionless piston. Let's say the area of the cross-section of the cylinder is A square centimeter. The pressure of the gas inside the cylinder is P, and the volume of the gas inside the cylinder is VI. Here, VI stands for the initial volume of the gas. Now, let's apply external pressure PEX on the piston. If the external pressure PEX is greater than the internal pressure P, then the piston moves inwards until the pressure P inside the cylinder becomes equal to the external pressure PEX. Let this change be achieved in a single step. At this stage, the final volume of the system is represented by Vf, and the distance that the piston is moved is represented by L. Thus, the change in the volume, that is, final volume Vf minus initial volume Vi, is distance L multiplied by area A. We know that pressure equals force divided by area. Hence, the applied force F on the piston equals pressure multiplied by area. That is, the applied force F equals external pressure PEX multiplied by the area of cross-section A. If W is the work done on the system by the movement of the piston, Then, work equals force multiplied by distance. But force equals external pressure. That is, PEX multiplied by area of cross-section A. Substituting the value of force in the equation for work, we get work is equal to external pressure PEX multiplied by area A multiplied by distance L. But distance L multiplied by area A gives change in volume delta V. On substituting, we get work equals external pressure PEX multiplied by minus change in volume delta V. That is, work is equal to minus external pressure PEX multiplied by final volume VF minus initial volume VI. The negative sign is added in the expression to obtain the conventional sign for W. According to the latest SI conventions, W is taken as positive if work is done on the system, that is, the work of compression. And W is taken as negative if the work is done by the system, that is, the work of expansion. Therefore, the general expression for work done is written as W equals minus external pressure PEX multiplied by change in volume delta V, which is equal to minus external pressure PEX multiplied by final volume VF minus initial volume VI. The expression of work applies for both expansion and compression of a gas. If the gas expands, VF will be greater than VI. Then, we can say that work is done by the system. Hence, the value of work done will be negative. Similarly, if the gas compresses, VF will be lesser than VI. On substituting the values of volume in the equation of work, we get a negative volume. When this negative value is multiplied with the negative external pressure, the resultant work is positive. Then we can say that work is done on the system. If the pressure is not constant and changes in finite numbers of steps for every stage of compression, then the work done is calculated as W equals minus the summation of pressure multiplied by change in volume. When these values are plotted on a graph, the work done on the gas is visible in the shaded area. However, if the pressure is not constant and varies such that it is always infinitesimally greater than the pressure of the gas at each stage of compression, the volume decreases by an infinitesimal amount dV. Then, work is equal to minus F integral of external pressure PEX multiplied by infinitesimal change in volume dV. If gas expands, then the external pressure is always less than the pressure of the system. Thus, PEX at each stage is equal to the difference between the internal pressure P and infinitesimal change in pressure of the system dP. If gas is compressed, then the external pressure is always greater than the pressure of the system. Thus, the PEX at each stage is equal to the sum of the internal pressure P and infinitesimal change in pressure dP. Therefore, external pressure applied on a system is expressed as external pressure equals internal pressure plus or minus infinitesimal change in the pressure of the system. This is known as reversible process. Thus, a reversible process is one that takes place infinitesimally slowly and the direction of which at any point can be reversed by an infinitesimal change in the state of the system. In a reversible process, the system is in equilibrium in the initial, final, and all intermediate stages. To understand this, let's assume that there is a cylinder with a frictionless piston. Now, let's place few grains of sand above the piston and allow the gas to compress by adding 1 grain of sand at a time. Here, the process is so slow that it can be easily reversed by removing 1 grain of sand at any time. This is known as reversible process. Processes which are not reversible are known as irreversible processes. Under reversible conditions, the relationship between work and internal pressure is written as reversible work equals minus integral of external pressure PEX with respect to infinitesimal change in volume dV. We know that external pressure PEX equals internal pressure P in plus or minus infinitesimal change in pressure of the system dP. Thus, on substituting the values, we get the equation reversible work equals minus integral of internal pressure P in plus or minus infinitesimal change in pressure of the system dP multiplied by infinitesimal change in volume dV. As change in the pressure and volume are infinitesimally small, their product is still smaller. Therefore, the product of infinitesimal change in pressure dP and infinitesimal change in volume dV can be neglected. Hence, the final equation is reversible work equals negative integral of P in multiplied by infinitesimal change in volume dV. Now, if we represent pressure of the gas P in terms of the ideal gas equation, then we get PV equals nRT or P equals nRT divided by V. On substituting the value of P at constant temperature in the reversible work equation, we get reversible work equals minus integral of nRT multiplied by infinitesimal change in volume dV by V. Integrating and applying limits as Vi for initial volume and Vf for final volume, we get reversible work W rev is equal to minus nRT ln final volume Vf divided by initial volume Vi. On converting natural logarithm to base 10, we get reversible work W rev equals minus 2.303 nRT log Vf by Vi. If the gas expands in vacuum, external pressure PEX being 0 in the expression W is equal to minus PEX multiplied by delta V, W becomes 0. This is known as free expansion. No work is done during the free expansion of an ideal gas, whether the process is reversible or irreversible. We know that according to the first law of thermodynamics, the change in internal energy is represented as delta U equals Q plus W. On substituting the value of W in the above equation, we get delta U equals Q plus minus PEX multiplied by delta V. If the process is carried out at constant volume, delta V is 0. Therefore, work done is also 0. Hence, at constant volume, delta U equals QV, where QV is heat supplied at constant volume. We have learnt that if a process is carried out at constant volume, then the heat content is the same as the internal energy as no work is done. But most of the chemical reactions are carried out at constant pressure and not at constant volume. When a reaction is performed under constant pressure, then it may involve change in the volume. The energy change occurred during such reactions may not only involve change in internal energy but also do some work. To understand this, assume a chemical reaction occurring at a constant pressure. Let us assume that the reaction is exothermic and also involves gaseous substances. When the reaction proceeds at constant pressure, two possibilities arise. One possibility is that if the reaction is carried out with increase in volume, then the system has to expand against atmospheric pressure and energy is required to perform this act. As some of the energy has to be utilized for this purpose, the heat evolved in this case would be a little less than the heat evolved at constant volume conditions. The other possibility is that if the reaction is carried out with decrease in volume at constant pressure, then the work is done on the system and heat evolved would be greater than the heat evolved at constant volume. Thus, it can be concluded that heat changes occurring at constant pressure and temperature are not only due to change in internal energy but also due to expansion or contraction against the atmospheric pressure. Hence, the scientists felt the need to study the heat changes at constant pressure and temperature. In order to study the heat changes in a chemical reaction at constant temperature and constant pressure, a new thermodynamic function called enthalpy was introduced. The total heat content of a system at constant pressure is equal to the sum of the internal energy and PV. This is called the enthalpy of a system, which is represented by H. Note that enthalpy is also called as heat content. Enthalpy, which depends on the three state functions, internal energy, pressure, and volume, is also a state function. Every substance has a definite value of enthalpy. Like internal energy, enthalpy of a substance cannot be measured. However, it is possible to measure the change in enthalpy. The change in enthalpy is equal to the difference between enthalpy of products and enthalpy of reactants. The change in enthalpy may be expressed as delta H is equal to enthalpy of products, HP, minus enthalpy of reactants, HR. The significance of delta H also follows from the first law of thermodynamics, as delta U is equal to QP minus P delta V. Here, QP represents the heat absorbed by the system and minus P delta V represents the work done by the system. Let U1, U2, V1 and V2 represent the initial and final internal energies and volumes respectively. The above equation can be written as U2 minus U1 equal to QP minus P into V2 minus V1. On rearranging this, we get QP equal to U2 plus PV2 minus U1 plus PV1. But we've already learned that U plus PV equal to enthalpy H. Hence, the equation can be written as QP equal to H2 minus H1 is equal to delta H. Therefore, delta H is equal to QP. For finite changes at constant pressure, we can write the equation as delta H is equal to delta U plus delta PV. Since P is constant, we can write as delta H is equal to delta U plus P delta V. Remember that delta H is equal to QP, the heat absorbed by the system at constant pressure. Delta H is negative for exothermic reactions and positive for endothermic reactions. Let's now look at the relation between delta H and delta U. When we deal with solids and liquids, the difference between the change in internal energy, delta U, and enthalpy, delta H, is not significant. This is because solids and liquids do not show significant change in the volume when heated. Thus, if change in volume, delta V, is insignificant, it implies that change in enthalpy, delta H, equals change in internal energy, delta U. The difference between the change in internal energy and enthalpy becomes significant when gases are involved in the reaction. Let's consider a chemical reaction occurring at constant temperature, T, and constant pressure, P. Now, let's say that the volume of the reactants is VA and the number of moles in the reactants is Na. Similarly, the volume of the products is VB and the number of moles in the product is NB. We know that according to the ideal gas equation, PV equals nRT. Thus, for the reactants, PVA equals NART, and for the products, PVB equals NBRT. Thus, PVB minus PVA equals NBRT minus NART, or PVB minus VA is equal to NBRT minus NART, or PVB minus VA equal to NB minus NART. That is, pressure P multiplied by change in volume, delta V equals change in number of moles of gas, delta N GRT. Note that delta N is the number of moles of gaseous products minus number of moles of gaseous reactants. We learned that change in enthalpy delta H equals change in internal energy delta U plus product of pressure P and change in volume delta V. On substituting the values, we get change in enthalpy delta H equals change in internal energy delta U plus change in number of moles of gas delta N GRT. This relation helps us in calculating the change in enthalpy from change in internal energy and vice versa. Now let's learn about heat capacity. The capacity to absorb heat energy and store it is known as the heat capacity of a system. The heat absorbed by the system appears as rise in temperature. The increase in temperature is proportional to the heat transferred, which can be written as Q equals coefficient multiplied by change in temperature, delta T. Note that the value of the coefficient depends on the size, composition, and nature of the system. The equation can also be written as Q equals C multiplied by delta T, where C is called the heat capacity of the system. If Q calories is the heat absorbed by the system and the temperature rises from T1 to T2, the heat capacity C is given by the expression C equal to Q by T2 minus T1. Thus, heat capacity is defined as the amount of heat required to raise the temperature of the system by 1 degree at a specified temperature. The specific heat capacity is the quantity of heat required to raise the temperature of unit of mass of a substance by 1 degree Celsius or by 1 Kelvin. Thus, the expression for Q in terms of specific heat capacity becomes Q equals specific heat capacity C multiplied by the mass m multiplied by change in temperature delta T. The molar heat capacity of a substance is defined as the quantity of heat needed to raise the temperature of 1 mole of substance through 1 degree Celsius or 1 Kelvin. The SI unit of molar heat capacity is Joule per degree Kelvin per mole. The molar heat capacity Cm equals heat capacity C divided by N, where N is the amount of the substance. Heat is not a state function, neither is heat capacity. Hence, it is necessary to specify the process by which the temperature is raised by 1 degree. The two important types of molar capacities are molar heat capacity at constant volume and molar heat capacity at constant pressure. Let us see the relation between molar heat capacity at constant volume, which is denoted by CV, and molar heat capacity at constant pressure, which is denoted by Cp. We learnt that the equation for heat, Q, is the product of heat capacity and change in temperature, delta T. Therefore, at constant volume, heat, QV, equals product of heat capacity at constant volume, CV, and change in temperature, delta T. But the heat absorbed at constant volume is equal to change in internal energy. Thus, CV into delta T can be written as equal to delta U. Similarly, at constant pressure, heat QP equals product of heat capacity at constant pressure, Cp, and change in temperature, delta T. We have seen that at constant pressure the heat absorbed by the system is equal to the change in enthalpy. Hence, Cp into delta T can be written as equal to delta H. The difference between Cp and Cv for 1 mole of an ideal gas can be derived as follows. The change in enthalpy for 1 mole of an ideal gas can be written as delta H equals delta U plus delta PV. For 1 mole of an ideal gas, PV is equal to RT. Hence, the equation can be written as delta H equals delta U plus delta RT. As R is constant, the equation can also be written as delta H equal to delta U plus R delta T. On substituting the values of delta H and delta U in the equation, we get Cp multiplied by delta T equals Cv multiplied by delta T plus R delta T. Since delta T is equal to 1, we can write the equation as Cp equal to Cv plus R, or Cp minus Cv is equal to R. Calorimetry is an experimental technique that involves the measurement of heat changes associated with physical or chemical processes. In laboratory, such changes are measured in a calorimeter. These measurements are generally carried out under two conditions: at constant volume, QV, and at constant pressure, QP. The experimental technique of calorimetry actually involves two steps. First step is the determination of heat capacity of a calorimeter. The second step involves the determination of the change in temperature during the completion of the reaction, assuming that it is an insulated system and no heat is exchanged with the surroundings. Let us first discuss the measurement of heat change at constant volume, or the internal energy change, delta U. The reactions that can be most easily studied under constant volume conditions are the combustion reactions, and the apparatus used for this purpose is called the bomb calorimeter. It consists of a sealed constant volume steel container known as the bomb, in which the reaction takes place. The bomb can withstand high pressures. A known mass W grams of a combustible substance is placed in the bomb, and oxygen under high pressure is introduced into the bomb. The sealed bomb is then immersed in a known amount of water contained in an insulated container. As the container is insulated, there is no heat exchange with the surroundings, and the reaction process is adiabatic. This whole setup is called the bomb calorimeter. The sample is ignited electrically, and the heat produced by the combustion reaction is absorbed by the water surrounding the bomb. The increase in temperature of water, delta T, is noted, and the heat produced is calculated using the equation QV is equal to CV multiplied by delta T, where CV is the heat capacity of the calorimeter. The measure of a bomb calorimeter's heat-absorbing property is called its heat capacity. Each bomb calorimeter differs from all others in its ability to absorb or release heat. The heat capacity of each bomb calorimeter is determined experimentally. Heat capacity of the calorimeter is determined separately by igniting a known amount of a substance, whose heat of combustion is already known, in the same calorimeter. And CV is equal to C multiplied by M, where C is the specific heat of water and is equal to 4.184 joules per Kelvin per gram, and M is the mass of water. Actually, heat capacity of the calorimeter or the system is the sum of heat capacity of the bath, that is, water, and the heat capacity of the bomb, that is, the metal. Water has high value of heat capacity as compared to the metal of the bomb. Thus, heat capacity of the metal is neglected, and the heat capacity of the calorimeter is taken as the heat capacity of only the bath. This QV expressed above is the heat evolved when combustion of W grams of the substance takes place. Since heat of combustion is defined as the combustion of 1 mole of a substance, therefore, the expression for molar heat of combustion becomes molar heat of combustion is equal to CV multiplied by delta T multiplied by M by W, where W is the mass of the substance taken and M is the molecular weight of that substance. As the above reaction is carried out in a closed vessel, therefore, heat evolved is the heat of combustion at constant volume and is a measure of internal energy change, delta U. Let us now measure the heat changes at constant pressure. To measure the heat changes at constant pressure, a device known as a coffee cup calorimeter is used. These calorimeters are open to the atmosphere, so these measure heat changes at constant pressure. This calorimeter is a foamed polystyrene cup partially filled with a known volume of water and fitted with a stirrer and a thermometer inserted through the lid of the cup. When a reaction occurs in the coffee cup calorimeter, the heat change is measured in terms of the change in the temperature of the system. Heat flow in the system is calculated by using the relation Qp is equal to specific heat multiplied by m multiplied by delta T, where Qp is the heat flow in the system, m is the mass of water in the coffee cup in grams, and delta T is the change in temperature. Specific heat of water is taken as 4.184 joules per Kelvin per gram. Therefore, the formula for calculating molar enthalpy delta H substance is delta H is equal to m multiplied by specific heat of water multiplied by delta T divided by N, where N is the number of moles of the reacting substance in the system. It is important to note that when heat is absorbed or evolved by the system at constant pressure, we are actually measuring changes in the enthalpy. Therefore, delta H is equal to Qp. In an exothermic reaction, heat is evolved and the system loses heat to the surroundings. Therefore, Qp as well as enthalpy change delta H is negative. Similarly, for an endothermic reaction, heat is absorbed by the system from the surroundings, and therefore Qp as well as the enthalpy change delta H will be positive. The enthalpy change that accompanies a reaction is called reaction enthalpy or enthalpy of reaction. The enthalpy change that accompanies a reaction is called reaction enthalpy or enthalpy of reaction. The enthalpy of a reaction is defined as the amount of heat evolved or absorbed in a chemical reaction when the number of moles of the reactants as expressed in the chemical equation have completely reacted. Enthalpy change of a reaction is denoted by delta RH. Enthalpy of a reaction is expressed as the summation of enthalpies of products minus the summation of enthalpies of reactants, where AI and BI are the stoichiometric coefficients of the products and reactants respectively in the balanced chemical equation. For example, the enthalpy changes for the reaction of 1 mole of methane with 2 moles of oxygen forming 1 mole of carbon dioxide and 2 moles of water may be represented as follows. The knowledge of reaction enthalpy helps us in maintaining the conditions required to carry out the industrial chemical reactions at constant temperature. It also helps in calculating the temperature dependence of equilibrium constant. The enthalpy of any reaction depends on the conditions under which it is carried out. Thus, it's difficult to compare the enthalpy reaction value for different reactions. To overcome this problem, the values of delta H for different reactions are expressed at their standard state conditions. The standard enthalpy of a reaction is the enthalpy change accompanying the reaction when all the reactants and products are taken in their standard states. A substance is said to be in a standard state when it is present in its most pure state under a pressure of 1 bar at a specified temperature. In other words, when the enthalpy of a reaction occurs at 1 bar pressure and specified temperature, it is called standard enthalpy. For example, the standard state of liquid ethanol is pure liquid ethanol at 298 Kelvin and 1 bar pressure, and the standard state of solid iron is pure iron at 500 Kelvin and 1 bar pressure. Let us now look at the enthalpy changes during phase transformations. We know that the intermolecular forces in the 3 states of matter are different. Therefore, the amount of energy required to convert matter from one state to another also differs. Standard enthalpy is represented as delta H naught, where the superscript naught indicates the standard state. The process by which matter is converted from one state into another is known as phase change or phase transition. The enthalpy or heat changes accompanying these phase changes are enthalpy of fusion, enthalpy of vaporization, and enthalpy of sublimation. Let's look at each type in detail. Standard enthalpy of fusion is the enthalpy change accompanying the melting of 1 mole of a solid substance in standard state into its liquid state. It is also called as molar enthalpy of fusion and is represented as delta fusion H naught. For example, the amount of heat required to melt 1 mole of ice at 273 Kelvin is 6 kilojoules. Thus, we can say that the molar enthalpy of fusion of ice is plus 6 kilojoules per mole. As the melting of a solid is an endothermic process, all enthalpies of fusion are positive. We know that freezing is the reverse of fusion. Thus, the enthalpy of freezing, also known as enthalpy of solidification, is the same as enthalpy of fusion, except that it has the opposite sign, that is, a negative sign. Now let's look at the enthalpy of vaporization. The amount of heat required to convert 1 mole of a liquid into its vapor state at constant temperature and under standard pressure is called its standard enthalpy of vaporization or molar enthalpy of vaporization. For example, the amount of heat required to convert 1 mole of water into vapor at temperature 373 Kelvin is 40.79 kilojoules. Thus, the molar enthalpy of vaporization of water is plus 40.7 kilojoules per mole. We know that condensation is the opposite of vaporization. Thus, the enthalpy of condensation has the same value as the enthalpy of vaporization, except that it has the opposite sign, that is, the negative sign. Now, let's look at the enthalpy of sublimation. Sublimation is a process in which a solid changes directly into vapor state without any intermediate liquid state. Enthalpy of sublimation is defined as the enthalpy change accompanying the conversion of 1 mole of a solid directly into vapor phase at constant temperature and under standard pressure. For example, the amount of heat required to sublime 1 mole of iodine is 62.4 kilojoules. Thus, we can say that the molar enthalpy of sublimation of iodine is plus 62.4 kJ per mole. The magnitude of the enthalpy change in phase transformations depends on the strength of the intermolecular interactions between the molecules in the substance undergoing phase change. For example, it requires about 40.79 kilojoules of energy to vaporize 1 mole of water, while it requires only 29 kilojoules of energy to vaporize 1 mole of acetone. This can be explained in accordance to the fact that the water molecules are held together in the liquid state through hydrogen bonding, while the acetone molecules are held together only through weaker dipole-dipole interactions. Thus, it requires less heat to vaporize 1 mole of acetone than 1 mole of water.